What's up, everybody? Welcome back to the channel. We got the 59 CJ5 F-head. This is going to be part 4 of the engine rebuild series. Now we're going to go ahead and do the inspection. I've already inspected everything off camera. I'm just going to go over the whole process on what to inspect, how to inspect it, etc., etc. Just still got to do a little bit more cleaning up on this deck. I had it real nice and shiny, and you know, even after a coat of WD-40 and some oil, it kind of dirtied up again. But anyway, so the first thing we're going to do is we're going to check the deck for straightness, make sure it's not warped, everything like that. So basically, get you a straight edge, and you're going to go ahead and put it basically an X, and then put you a flashlight behind here, see if you see any light shine through. If you're unsure, get you the thinnest feeler gauge you have, you know, like a 1/1000th, maybe you have one thinner, run it in there and see if it's all consistent. And we're going to do the same thing on this axis here. Do about midpoint of the bores, do right after the bores, and then just off the edge. So this deck's perfectly straight on this, which is not very surprising. These engines run real cool, you know, not a lot of heat going through them, and not a lot of pressure and stuff, and it's a real thick casting. Next thing we're going to do is we're going to inspect the bores. Before we inspect the bores, the process for the head is the same way. You know, just lay your head over, check it with the straight edge. Same process. So now for the bores, the lighting. There we go. So these bores got a little dirtier. Hopefully. These bores still look pretty good. They're a little dirty. Number 4's got a little bit of corrosion on it, but nothing crazy. Oh, this damn tripod broke on me. Anyway, so normally when you have a real high mileage engine with a lot of wear, you'll have a carbon ridge here. So basically what that is that's a buildup of carbon that's going to be sticking out farther than the bore. So what that is let me grab a piston. So here on your piston, your top ring ends right here. So all this is dead space. So when your piston's all the way up, I don't want to drop it. You know, only all this up here is exposed, and that builds up carbon. So when that happens, you'll have to, depending on the severity of it, you can hone it out. But in most cases, if it's real severe, you have to get a ridge reamer. So yeah, these bores look good. We're going to go ahead, before we start measuring and stuff, we'll go ahead and inspect. Go ahead and inspect the crankshaft, the connecting rod bearings, and the main bearings, and then we'll do measurements. Here we have the crankshaft. Here's the rear. What you want to check for is excessive gouging. So I already polished this crankshaft. It had a little bit of gouging. I never filmed it. But basically your wear, you know, if your fingernail gets caught on it, it's normally a sign it's too much. And then we'll go ahead and do the measurements on it as well. But I just wanted to show you this crankshaft's going to be good to put back in without having to take a visit to the machine shop. So all right, so here's our connecting rods. These just came out of the parts washer a little bit ago. Went ahead and cleaned this one twice. These are going to all get cleaned about 3 times. So We will weigh these later. We're going to weigh the connecting rods and the pistons just to kind of get kind of, you know, a guess on how balanced everything's going to be. But we'll just do a quick bearing inspection. So this is the rod, connecting rod bearing. This is the one that goes on the rod. See, not too bad. Looks like oil was a little dirty. And here's the cap, so this is the bottom. You can see a little bit more dirt damage. No really heat checking or anything, just seems like a lot of debris in there. This one's number 1. You can see a little bit more gouging and debris damage. Cap forward as well. And then on number 2, we got a little bit of flakes going on. So it seems like this was a little bit in between oil changes for a while. Pretty dirty. And this bearing has a little bit of material missing on it. This one's number 4. So, and also here's the cap for number 4. You can see where something drug. So, but all in all, the crankshaft was okay. You know, it just came out a lot better doing a quick polish on it. I'll go over, well, so to polish on the crankshaft, I just used a buffer with medium fine buffing compound, then went over it with 1000, 1500, and 2000 grit sandpaper, and gave a pretty good finish. So moving on, here we have our intake valves. So here's one of them. You can see how much carbon buildup is on there, and also the valve face itself. Not a whole lot of wear on the valve face compared to the exhaust valves. These just don't see the higher heat like the exhaust valves do. One of the big flaws with the L head and F head engine is, here's the exhaust valve, is, you know, the exhaust valve gets caked in the block. You know, all that heat just holds in the block, and then, you know, the exhaust manifold's right there and everything. So these get pretty hot, but all the valves are getting replaced. I just wanted to show you, we got kind of a lip there that's supposed to be a straight angle, so those valves are no good anymore. I mean, if you really wanted to, you're on a budget, couldn't afford to get new valves, you know, you could probably get away with lapping them, but you know, you probably have some running issues. So moving on to the pistons. This one cleaned up real nice, measured it, so it's gonna fit nicely in the bore. I'll go over measuring here later in this video. But basically, you just want to make sure your top carbon ring's cleaned out, all your ring lands and grooves, and then also these holes here are cleaned out. And then your wrist pin slot, make sure, inspect for cracks, all that good stuff. And also on the inside, you know, because you got all your explosion happens up here. So if you don't see any cracks here, just give it a peek inside there. And then also the wrist pin area for cracks, etc., because these are just aluminum. Here's the number 4 piston. It's got a little bit of debris damage on it. It cleaned up real nice. We're gonna just reuse it instead of you know, putting in another used piston. But same deal, just clean out the grooves and everything. So the one thing to check on your camshaft is going to be your cam gear. This one's going to be reused. Aftermarket one's pretty expensive and kind of unsure on the quality. I'm still running the original cam gears on both of my engines. But this journal here, this is what there's only one cam bearing. I'll go over that here in a minute. So the cam bearing rides on this, and then these other 2 journals just ride in the block, and the bearings are non-changeable other than the front. So these just ride on basically a boss inside the engine. Cam lobes, you can see this is the exhaust lobe here. a lot of lift and no duration. Pretty unusual. Normally have more duration on an exhaust valve on a newer engine, and then you can see the more broad lobe on the camshaft for a little bit more duration on the intake side. But yeah, all these cam lobes look really good. You just want to basically inspect, make sure there's no nicks, gouging, you know, make sure cam lobe's not wiped out, flat, you know, anything like that. So nothing wrong with this cam. It's going to get put back in, going to have no worries with it. And then also here, this is your oil pump drive gear right here. So looks good. So now we'll go ahead and move on to measuring stuff. We'll just start with the cylinder bores. I'll show you what I do with those, how to do those, and then the crankshaft's going to be pretty involved. I'll try to simplify it as best I can. Okay, so for measuring the bores, just get you a piece of paper. What I like to do is number it, and then I'll draw out the cylinders. I got an arrow facing front, so we're just only going to take two X and a Y axis. So we're going to do top of the bore and bottom of the bore. So I'll add two. I just got to draw another set of circles. Forgot to. Basically, tools you're going to need at minimum are telescoping gauges. So telescoping gauges come in different sizes. Just find the right size that you need. This one's I think a 2.5 inch to a 3 3/4. These standard bores are 3 1/8 is a standard, so that'd be 3.125 on a decimal system. Here is a dial bore gauge. You can use this as well if you have it. I'm going to use both just to verify the measurements. So we'll come back to this. And then also a 3 to 4 inch micrometer with a vernier scale that goes down to 10 thousandths. That's very important, especially when we're doing the crankshaft and bearing clearances. So basically the telescoping gauge, I'll demonstrate it again when we go to do it. You're just going to press it in, twist this. This is going to spring out, hit the bore, and you want to make sure it's perfectly straight. Then we're going to pull it out, measure it with the micrometer, reset it, do another measurement this way, measure it further down at the bottom of the bore, spin it. There we go. So we're going to have a total of 4 measurements per cylinder. So for the dial bore gauge, I'm not an expert on dial bore gauges, so if there's any machinists watching, I'm sorry. But basically you have the standard here. I got some spacers in here. It's about, I think, like 50 thousandths larger, so I think it's 45, so it's 3.165. But basically what this does is this goes down, this springs back, rides your cylinder, and then this is going to move. Your anvil is going to stay, and your dial indicator is going to move. So we'll go ahead and we're just going to use this to confirm. We're just going to use both, and I'll explain it. But basically, so for me to get 3.125, this will read 40. So we'll subtract whatever this says. We'll subtract that number off of 3.165. I got 6.6. It's about 1,000ths off. It was kind of hard to measure in the micrometer, but 3.165, and then we'll subtract that, and then that'll give us our bore measurement, and we'll see if they all match up. So I'm gonna go ahead and move the camera, and we'll get started. All right, so we're gonna start with the telescoping gauge. So we're gonna go ahead and get it in the center of the bore, spring it out, and you want to make sure you go past the very top, because remember the very top is going to have no wear on it, or have a carbon ridge. So just go about 1/2 inch off the top, make sure it's straight, just move it around, make sure the spring isn't stuck. So we got it straight. It might look a little off center on the camera, but it's straight. And then we got it lined up with the center of the bore. So go ahead and tighten it up. So now I got my micrometer ready. I'm going to try to do this on camera. It's just tight spaces. So on the telescoping gauges, you just want to do it till it clicks. So you're going to use the thimble. So go ahead and lock her down. So we got 3.12. So we're in between the 6 and 7. We'll go ahead and round it up to 7. So 3.127, and then we'll check our 10,000ths. Oh shit! Oops. Pardon my language. Let me redo that. I thought I had it locked, and I was wiping the oil off. It's just hard with the dang camera in the way. Here we go. Let's see if it's the same. Alright. So yeah, 3.127. Then our 10,000ths. So you'll see, hopefully the dang, it looks smudged on my end. So you just find the line that lines up with your 10,000ths, so it's 8. So I'm gonna go ahead and write that down. We got 3.1278. So that means we have 28 10,000ths wear on the board. So that's 2.8 thousandths. I'm not an expert on decimals, so that's really not that bad. You're allowed all the way up to 9 thousandths to run standard rings, or not standard, but the same size. So if this was bored 10 thousandths over, it'd be 135. So we'd be allowed up to 144. So to use that same ring size. This is still standard, so it's going to get standard rings. And it's going to be basically the same thing. We'll just do this measurement. I'll do it off camera. And then further down. So, but further down in the bore, you're going to see where the cross hatching gets a lot more predominant down there. That's where the piston stops its travel. So there's going to be no wear all the way at the bottom. So you want to do it about ½ an inch up from where you see your wear mark. Because you'll get a false reading if you go all the way to the bottom. And you'll think you'll have a real tapered bore when in reality you just measured the wrong spot. So we'll go ahead and... Alright, so I got the dial bore gauge. So I'm going to go ahead and we'll compress it, put the anvil down. And then, here, let me move the camera. Here we go. Hopefully the glare is not too bad. So you're just going to move this back and forth. You'll see how I'm changing it, how the... I'm not an expert at a dial bore gauge. I've always used telescoping gauges, but figured I'd get fancy and use one of these too. So you can see how it's moving. So we're going to go ahead and just hold it straight. It looks pretty straight. So this is in ½ thousand. So that's 35, then 35.5, and then 36, 36.5, 37. So we'll go ahead and round that up to 37. We'll go ahead and write that down and then subtract that from our 165 and see if our telescoping gauge is close. All right, so telescoping gauge, we got 3.1278, and the dial bore gauge, we rounded it up, so we got 1280. So we're within 2 10,000ths, and realistically I rounded up, so both of them are right on the money. So we're roughly 3 thousandths of an inch wear. So now I'm going to go ahead and measure the other axis. So go ahead and measure this way, and this is going to check taper. So we're allowed 1/1000ths taper, which is pretty tight. I mean, you know, that's not a lot, especially when you're talking about a circle. So if it's a little over will probably allow it. And we'll go off our piston measurements too. So, alright. I'm just going to go ahead and micrometer it off camera real quick, speed it up. That's not good. Let me redo that. That wasn't a good measurement. Yeah, make sure you're everything's straight. You're in the center, and then roughly the same length down, about that 1/2 inch. Alright, so on that we're at 9/10 thousandths, so that's almost 1/1000th. So we're just on the cusp of being out of spec. But like I said, that's a pretty tight margin, especially for an engine design that's 70 years old. I guess, you know, there's higher standards. So I'm just doing the same thing we just did, just off camera, so I don't have to reset up the camera. So 36 again. Oh no, we had 37. So it's going to be 3.1270. So once again we're within a 10,000ths of the telescoping gauge. So it's pretty consistent. So we're almost a thousandths out around 9/10 thousandths. Shouldn't have an issue with that. So the reason to get egg shaped and oval shaped is because the thrust on your piston and connecting rod. So your piston and connecting rod's coming up, and when that crankshaft, so your crankshaft is on an inline, you know, going this way, so it's putting more pressure on your sides, because that'd be your thrust, because you have your pin, your wrist pin and everything. So it's going to cause more wear on one side and the other, and that's how you get your egg shape. So, all right, I'm going to go ahead and measure the rest of them, and we'll go over the results. All right, so I got the cylinders all done. We'll go over those measurements here in just a minute. But before we go over those, we're going to go ahead and measure piston. So real quick on a piston, so your very top is going to be a different measurement than your ring grooves, and then also your skirt is going to be different. There's a slight taper to it, so I'll go ahead and demonstrate that now. The only measurement that really matters, in my opinion, this can vary, is basically the ring grooves. So go ahead and take our micrometer. Now these are going to be smaller than your bores, so we'll just go ahead and lock it on the top groove. A little hard to do on camera. All right, and you could just use the hole to, you know, line everything up. So this one is number 3. So I went ahead and measured, crap, I got to redo that. I forgot which way I measured it. So the wrist pin side, so this is the front of the engine. The wrist pins is going to be this way. So that's going to follow our bore measurement. So that's how I have it written on here. So basically, when I'm looking at my bore chart here, that's how it's going to read. Let me go ahead and redo this. I measured a couple of these. I haven't measured number 3 yet, but I'm starting this chart over by scratch just to demonstrate. So just move the micrometer back and forth a little bit, make sure we got a good reading. So that was the wrist pin side, so it's going to be this one. So we got 3.077. Make sure I got that right. Yep. Oh no, crap, that's number 3. Hold on. Alright, so that means we'll go ahead and take our measurement from cylinder 3 on that same axis. So we had on the top, we had, excuse me, 3.1283. We'll just call it 3.128. So it is, my math is terrible. So 100, so basically 1/8 of an inch. So the pistons are about 1/8 of an inch smaller. So we're good on that. Basically, while I'm measuring the pistons, to make sure they're not too out of round, and if they are, that they're pretty comparable to what our bore dimensions are. So, like on cylinder 3, we had no out of roundness. I measured it a couple times, verified it with the dial indicator on our top, and then our bottom, we had 6/10,000ths of bore taper. So if we're pretty close on our piston and we know everything's good to go, that's why, you know, you don't really have to do this. I'm just doing it just because it's the right thing to do. You could just slap this back in there as long as your bores measure out good and, you know, send it. But I just want to be real detailed with this. So now we're done with the piston, and you'll just go ahead and do your other access. So you have, you know, both. Damn it. Which we'll probably just go ahead and do right now, so we can just see it together. Like I said, I haven't done this one yet, because I'll go over in a second why I stopped. So this one we got 3.0678. I know this is probably pretty boring, but hold on, I missed a number. Oops. Sorry about that, guys. I screwed up. I read the damn micrometer wrong. Okay, so there needs to be a 1 in there. It's been a long day, as usual. Okay, so now they're not 1/8 of it. They're not what I said. They are. So we just take 128. And then minus 107, that's 27, right? No, 21. Yep, 21. So 21,000 smaller. If I'm wrong, correct me. My brain's fried today. But anyway, now you can see the difference on their piston. So the rest of that gap's filled up by the rings springing out, and all that good stuff. So our out around this, we're at 4/10,000ths. So, which is actually damn close to what our out of roundness is on the board. So we got 1283 and 1278. So that's 5/10,000. So we're good to go. So it's been a hectic time, and I can't remember if the previous video, if I mentioned the piston fiasco. So this is number 1 piston. Notice the difference with it between number 3. Oh, what's that? So this is an very old aftermarket piston. It's made by Alcoa. Don't know if they're still in business. Never heard of them. Some point in time in this Jeep's life, it's had a piston replaced and also a connecting rod. When we go to weigh the connecting rods to go over, but there's basically a remanufacturer stamp on it. They're Willys. They're all Willys connecting rods, but this piston's aftermarket. So this is telling me that this thing's had a piston put in it for some damn reason, and also a connecting rod, and it was number 3 connecting rod. So it doesn't really make any sense. So it's been, and I talked to the owner and his father that apparently they've had it since 1964. So basically new. It's a 59. So I guess between that 5 years of them not having it, this thing had some kind of catastrophic failure. Also, the crankshaft's been machined. Also, we'll measure that, but basically it's 20 thousandths undersized on the mains and 40 thousandths undersized on the crank pins for the connecting rod. So the crank's been turned. There's been a piston put in it and a connecting rod. So something happened. All right, so I'm getting kind of low on battery, so this is going to pick up. It's going to be in the same part, but another day. It's a little behind the scenes. All right, so we'll see. So now we're going to take our top and our bottom, and that'll be our taper. So for number 4, we got 1281 on the top, on that axis, and we got 1289. So we got 8 10,000ths taper, and for the bottom we got 1289. So we got 8 thousandths out of round, or 8 10,000ths. I'm sorry, out of round. And then that taper is 3 10,000ths. So we're on the cusp of spec of the 1,000ths out of round spec, but like I said, that measurement I kind of don't agree with. And our pistons are matching up pretty good. So them rings are gonna. I'm using old, just standard cast iron rings. I'm not putting chrome rings in. I think chrome on these boards is going to be a little bit too hard, especially with us not getting them machined, because I don't justify getting machined and bored out 10,000ths. But anyway, that's basically what I do. Hopefully, this answers some questions. And if you guys have any issues or anything, just give me an email. So now we're going to go ahead and do the fun part, and that's doing the crankshaft. So on the crankshaft, I'll draw it up on the paper, but you want to we're going to check overall diameter and also out of roundness. This also is maximum allowable is 1,000ths out of round, which is also a very fine number. So you're going to take it here. I'll just go ahead and draw it out on the paper. Like I said, I'm running out of space and battery today. So you're going to take measurement here, measurement there, measurement at 45. So you're going to take two 90-degree measurements. You're going to take a 45 and another 45. So you're going to have 4 measurements per journal. So there's going to be a lot of miking to do. I've already done it, so I guess we'll just go ahead and walk that through real quick. It's going to be the same. Reading the micrometer is going to be the same way we did for the bores. So for these, you're going to use a 1 to 2 inch mic, and for the crank pins, and then on the mains you can use a 2 to 3. Now with my stand to measure the mains, I just stood the crankshaft up. I'm not going to do it on camera because I already did it, and it was kind of wobbly and everything. With the dowels, because I don't want to remove the dowels, risk cracking the flange. There's no reason to remove them. We're just going to go ahead and turn it. And I got the wrong mic. There, go ahead to 2 to 3 out, not the 1 to 2. So just take it till it stops. You'll hear that click, because if you don't use the clicker and do this, you can risk you'll nick the crankshaft, and also you can stretch out the crane of the micrometer. So that would be this measurement when you draw it out. So alright, so these are all my measurements. So we're doing the crank pins first. So we'll just take number 3 crank pin, which is the other one. I measured number 4 just now. So we got 1.8978 on the one axis, and on the other we got 1.8971. So we got 7 10,000ths out of round. So we're still within spec. So now the factory standard crank pin ranges from 1.9383 and 1.9375. So that means if we take that, that means it's been cut down 40 thousandths. So there's been 40 thousandths removed on this crankshaft from standard. Also, these old bearings, these have a rubber stamp, so it says .40. So these would be a 40 thousandths undersized bearing. So under meaning 40 thousandths smaller than stock. So, and if we take, oh, I'm getting ahead of myself. So yeah, if you can't read the stampings or anything on your bearings, mic your crank and just subtract that from the standard spec, and that will give you your how much the crank's been machined, and get the correct undersized bearings. And then for your mains, you got standard is factory is 2.3331 and 3341. So you got 1/1000ths. They vary 1/1000ths from the factory, and on that we have 2.3148. So that means it's been cut 20 thousandths. So we have a 20 thousandths undersized main bearing. So now the next thing we're going to do, since we're on the crankshaft, now that hopefully you guys know how to measure the crankshaft, just take, you're going to take 4 measurements, 1, 2, 3, 4. Okay, so we're going to measure the main caps. So I had the main caps installed, torqued with the old bearings, and we're going to measure those. You don't have to do this, but we're going to measure those and take our actual measurement off the crank and the measurement of the bearings, and that's going to give us our oil clearance. So it's going to give us a good judgment on to make sure our measurements are all within spec, and also the oil clearance. So if the oil clearance is way out of whack, that means you measured something wrong, or the bearings are just that wore out. We'll do a bearing inspection when I flip the motor over and everything, and we'll do that next. All right, so now I got the engine turned over. Now we're going to check the. Now this is strictly optional. I'm just showing you how to do it. So if you want to, just double check everything. If you're not getting the machine cranked and all that stuff, or the crank machined, you can check your oil tolerances by measuring the inside of the bearing, and then subtracting that measurement. Subtracting your crankshaft measurement by your main cap measurement, and that difference will be your oil clearance. All right, so it's going to be the same principle as measuring the cylinder bores. You're just going to take a top and a side. You have your oil supply holes are going to get in the way. So you really just got to take one measurement. It's just kind of a reassurance baseline kind of thing, because these bearings are getting replaced, and the tolerance is going to be tighter from what we measure because of the new bearings. So another thing, if you take it to a machine shop, they can line bore it, make sure it's all perfectly straight. If you did have a little bit of twist, it could be bored out with a line bore. These things are pretty stout. I've never seen one that's been the crank bound up and all that good stuff. But all right, I'm gonna just go ahead and just measure it off camera real quick, and we'll just go over the measurement, and then we'll move on to we'll check out the tappets real quick, and then weigh the connecting rods and pistons. One thing I forgot to mention, also the cam bearing. There's only one cam bearing on these. If it's got multiple cam bearings, that means it's been line bored and bearings added. If you have low oil pressure issues and you tear the engine apart, and the crankshaft oil tolerances for the crank and the connecting rods are fine, then most likely you got a pretty worn out either cam bearing or the the journals that it rides on. If that's the case, then yeah, it'd have to be machined and then bearing inserts installed to tighten that up. Checking that's going to be the same way. Just measure it, and then you can just measure your journal that the cam rides on. So, all right, so I just rewrote it, but our actual crank main journal measured 2.3131, and our bearing cap measured 2.3117. So that is so that's 14 10,000ths of oil clearance. Hopefully I wrote that right. No, too many zeros. There we go. So we're well within spec. There's a wide range. It's the spec is 3 10,000ths to 29 10,000ths. So you're basically looking at thinner than a frog hair, all the way up to almost 3,000ths. So there's a huge span. That's pretty dang tight, especially with some wear on the engine. That's really good, and we will confirm that with plastic gauge when we get the new bearings installed. So what this plastic gauge does is, in the assembly, I'll do it again, but just in case y'all don't watch it, you just cut a strip of this and then you put it on the crank journal, then you clamp down and make sure everything's dry, and then torque down your main cap, and then remove the main cap, and then you just see how much the plastic's been crushed, and that tells you the bearing clearance. So ideally now, the smallest this goes down to is 1,000th. So if we meet that 1,000th, actually, yeah. So if we hit the 1,000th or smaller, if it goes water, then we're good. So, all right, we'll go ahead and check out the pistons and connecting rods, and then the tappet. All right, so I got the connecting rod stripped down, got the cap bolts removed, left the pin and the bolt in. We're just gonna do that. That way I didn't lose track of the pins. It's just one less thing to keep track of. As far as miking the pins go, if you had a real small inside bore gauge to check the connecting rod, you can, and then check the outside diameter. You can check the outside diameter for taper, but really the only part of the pin that's going to see any wear is the outside, where the piston rotates back and forth, and they're aluminum, so there should be no wear on these pins at all. So as far as weighing them goes, you don't have to. This is something, if you want a real smooth engine, it's good to know the weights, just to make sure, keep down on vibration, crankshaft harmonics, stuff like that, and just overall just better running engine. So we're going to start with number 1. Oh, scale timed out. There we go. So we're going to go ahead and put the cap on too. So we got 2 pounds 12 ounces, I think. Yeah, 2 pounds 12 ounces. So I'll go ahead and write that down. 2.12. All right, we'll get number 2. Actually, we'll just grab number 4. It's right here. And number 4 main cap, or connecting rod cap. So we got 210. Number 2. Check that one again. That one's a little light. Okay. Okay, 2.8. And then number 3. $2.12. All right. So we have number 1 and number 3 at 2.12, number 2 at 2.10, and number 4 at 2.8. So between our high and our low, we're within 4.4 ounces, which is good. All right, we go ahead and do the pistons. We got number 1. Hold on, let me make sure this thing's zeroed. Yeah, see, it's not zeroed. $13.4 ounces. Number 1. Number 2. 14. Sorry about that, I had a phone call. Number 3. 13.6. Another thing too, and while we're weighing the pistons is, you know, if you really wanted a really perfectly balanced engine, you could add weight to them, or remove weight, you know, whatever you see fit. The pistons, you really don't want to reduce weight. You can put weights like solder in. I've seen that done before, but our high was 14 and our low was 13.4, so we're within 0.6. The reason also I'm doing this is because this is the number 1 that came out of it. This is the aftermarket piston. We'll go ahead and weigh that. So that one's 15. So that's 1.6 ounces heavier. I know we're only dealing with ounces, but you know, you got an engine spinning upwards, you know, 4,000 is the red line on it. I mean, that can, and especially with how long the stroke is and how heavy these rods are, you know, I mean, look how long that is. You know, a small block V8, like a 4-inch bore, 4-inch stroke, like a 400. I mean, like a 350 Chevy or 351 Ford, a 4-inch bore and a 3.5-inch stroke. I mean, your rod's only that long. So, I mean, you can really see the size difference. I don't have any small block V8 stuff to show you comparatively because, you know, it's pretty popular. But yep, all these are good. I'm happy with them. There's no reason to take any weight away or anything. I didn't measure the bolts. Kind of irrelevant. They're all should be the same. I mean, we're dealing with fractions of an ounce probably of a difference. All right, so one last thing to do on the inspection is the tappets. So you can see I got all the tappets and push rods in here. This is my patent pending tappet lifter push rod organizer. I'm offering these free at Southern Jeep and 4x4. Any purchase you make, you get a free box. So that also doubles as a lifter and push rod organizer. So we got how these start out is your exhausts are on the outside. So we got 1 exhaust, 2 intake, 2 intake, 2 exhaust, 3 exhaust, 3 intake, 4 intake, 4 exhaust. So go ahead and we'll grab an exhaust, and you can just look at the surface. We still got a mirror-like finish. I mean, look at that reflection on there. These are cleaned. They're going to get cleaned again one more time. What you want to do to clean them, get any carbon buildup off. I wouldn't suggest Scotch-Briting them unless you have some nicks and burrs. If you Scotch-Brite this mirror finish, it's just going to dull it and, you know, not be as smooth. These adjusters do back all the way out. So there you go. You can kind of see it's like a split bolt setup, and you want to clean inside there with a brush. There's no escape for oil and crud, so you got to make sure you clean it real good, pour it out, clean it, pour it out, etc. And then reassembly is just going to get a little bit of light oil on the threads and then screwed back in. So when I clean them again, I'll go ahead and do that. So here we got an intake. This one has not been cleaned. So the intakes are non-adjustable on the F-head because you adjust it at the rocker arms like a conventional overhead valve engine. Our push rod pocket looks real good. Just some dirt in there that's going to clean up real nice, but the actual surface looks good, and then also the cam surface. So that's basically all for the tappets. And push rods, obviously you want to make sure they're not bent, so get a flat surface and roll them. You might just put them on the end of a table because you have this bell end here, so do it that way. If you try to do it, you know, it's not going to be level. So here's the actual mating surface that goes into your tappet. That looks real good. So, and then also the cup on where the rocker arm pushes down into. So yeah, all in all, this thing is about ready to be assembled. I'm just waiting on some main bearings. Had some issues getting parts for this. Personally, I recommend Clevite bearings. I have used Sealed Power in the past. They're owned by Federal Mogul, and you know, Federal Mogul owns a lot of aftermarket parts, and you know, you're gonna have failures, but it seems like I have a lot more Federal Mogul parts fail because I don't buy any of the house brand stuff like, you know, Duralast or anything like that. It's just junk. But yeah, I recommend Clevite. Also Hastings piston rings, made in USA in Michigan. Last I checked, these just came in today. These are March of this year production. They used to come in a rectangle box with individual pockets. Now they just throw them in these bags, which I'm not a huge fan of. But we're just using regular ductile iron rings. We're not doing chrome rings, especially with the bores being a little worn. They're not factory, you know, they're not fresh bores. So we want to just use iron rings. And then here's the connecting rod bearings. So I'll go over these again in the reassembly, but you can just see the quality on these Clevite bearings. I mean, they got a real nice surface, made here in the USA. It's just, that's the last two engine builds I've done, I've used Clevite bearings and they've been good. I have Seal Powered in my original CJ5, and they seem to be a little bit softer because I had to pull the oil pan off at one time, and I did a bearing inspection on it, and I wasn't very happy with the results. So, but anyway, that'll be more detailed in the assembly video. We're going to start on the assembly video. We're going to start off with the bottom end. We're going to work from the crank up. So it's going to be a lot of fun. But all right, if you guys have any questions, if there's anything I missed that you have a question on, hopefully I got everything. Feel free to leave a comment. My email's on the website. So, all right, have a good one.